So I actually did a test. And what distance does the umbra and penumbra start to happen using our sun? Well, the answer is...
That's right, folks. It's another Mr. Thrive and Survive video. I know I'm a little late to the game, but some of us have jobs to go to. Besides, I'd rather be detailed than punctual. Anyway, in a recent monumental pile of stupid, Mr. Thrive and Survive demonstrates his singularly unique inability to grasp the most basic concepts while arrogantly posing as an expert on those concepts. He is the living embodiment of the Dunning-Kruger effect. This time, he talks about how he thinks shadows should actually look and why the fact they don't conform to his misguided views proves something. The Earth is flat, NASA's lying. I don't know what he thinks he proves. It really doesn't matter because he doesn't prove anything other than his tenuous grip on reality. Anyway, strap in. It's time to start this shit show. The first thing Thrivey talks about is the size of the moon's shadow during an eclipse. He bangs on quite a bit without saying much, so I'm going to skip over that. Next, he compares the size of the shadow of our moon on Earth with that of Io's moon on Jupiter, and makes a complete balls of it. Let's watch this train wreck. See if you can spot where he goes completely off the rails.
If we had a satellite picture like we had with Jupiter, what would that look like? There we go. Look at that. Little teeny little dot. Little teeny Rosanna, Dana. Look at that. Now, let's compare that to Jupiter. Yeah, there's a little bit difference, huh?
Yeah, there's a little bit of a difference. Let's examine the reasons for this. First, he's only showing a portion of Jupiter, a smaller portion than he appears to realize. Let's look at the original NASA photo of the eclipse and a photo of Jupiter. The first thing you'll notice is that Thrivey's photo isn't all of Jupiter. Even the most brain-damaged flat earther couldn't fail to notice there's some very clear and obvious fisheye distortion in it. So, roughly how big would Io's shadow be on the full image of Jupiter? This is obviously the red spot in both images. There's a blue band above this, and the shadow is in the reddish band above that. It's difficult to determine the exact location where Io's shadow would be, but it would be approximately here. The size at this point is just a guess. I'll work it out in more detail later. We can compare that with the size of the Earth. Thrivey will probably complain that this is still a lot bigger than the 70-mile shadow that our moon casts on the Earth. Yes, it is. So now I need to calculate the size of the umbra of Io's shadow on Jupiter. To do this, I need to know the angular size of the Sun from Jupiter. The radius of Jupiter's orbit averages 7.78 times 10 to the 11 meters, and the Sun's radius is about 6.96 times 10 to the 8 meters. Basic trigonometry gives us the angular size of 0.102 degrees. With a little math, this means that, by extension, the umbra of Io's shadow will reduce in size by about 1.78 kilometers for every 1,000 kilometers away from the moon you go. Io's average distance from Jupiter is 351,789 kilometers. This means that the umbra of Io's shadow is about 626 kilometers smaller than Io. Io's diameter is 3,660 kilometers, so the diameter of the umbra would be about 3,034 kilometers. This would make the size of Io's shadow about this, which isn't too far off from my original estimate.
But let's compare Jupiter's size to the Earth. Here we go. Look at all these Earths that can fit into the side of Jupiter. All right. So how big would the speck be?
I believe I've already showed that. The speck would be exactly what's shown in NASA's photo. Thrivey yaps on a bit about Jupiter. Nothing I haven't covered already, so I'll just skip past that.
Umbra penumbra. Let's get into that, because this is the heart of the meat of the matter right here.
Great, we're starting to get to the point.
Okay, back to the video that was sent to me. Now granted, this is going to sound a little weird pulling in the Kennedy assassination here, but just think of the narrative that was given that people believed simply because they would not trust what their senses and logic told them. Now I'm not going to show it, but almost everybody probably listening to this video, watching this video, has seen the assassination of Kennedy, where he was shot and his head went back and to the left, and the front right part of his head was blown off. And yet, because the government said that it was a lone assassin in the back, this guy right here, Lee Harvey Oswald, just because the government said that, most of the people believed it, and the CIA came up with the term conspiracy theory to degrade anyone who actually wanted to use their logic. You see, logic tells you that if your head goes back and to the left, that means you were shot in the front right.
A little off topic, but okay. It's a lucky thing we don't blindly rely on our common sense. It's easily fooled. If you watch the original footage, I won't show it here, you will see blood spray out of the front of his head, indicating that it is an exit wound. In other words, the bullet came from behind, not in front.
What can our logic tell us about the umbra penumbra? Are we making an assumption that just like the Kennedy assassination, that what the government tells us, and NASA is most definitely an offshoot of the government, just because what NASA tells us it's true, even though, do our senses tell us this? Do we just accept everything blindly?
Why does this idiot think NASA or the big bad government is telling us how shadows work? This is basic elementary school science. A light is completely covered, full shadow. A light is partially covered, partial shadow. Not what I would call a difficult concept to grasp.
Here's the argument. It's always because the sun is larger. Because the sun is larger than the object that is blocking the sun, we get this umbra penumbra effect.
Wrong again. Because the sun is larger than the moon, the umbra is smaller than the moon. If the sun was smaller than the moon, the umbra would be larger than the moon. So, from the fact the area of totality of the eclipse was smaller than the moon, we know that the sun is larger than the moon. For clarity, I'm not showing the lines that define the penumbra because that might hurt Thrivey's fragile mind.
And particularly the effect we get with the the solar eclipses. And we have the shadow, as you can see here, comes down to a point, and then it goes the other way. Totally ridiculous, but we're not going to get into that. I've gotten to that in other videos.
Yes, you are totally ridiculous. The shadow doesn't come to a point. That's not what the diagram is indicating. The diagram only illustrates where the shadow from the pink circle would be, nothing else. Those lines just represent rays of sunlight, not the size of the shadow. Let's consider what the sun would look like for people standing in various places on Earth. First, consider a person standing between the two inner lines. The sun is completely blocked from view. This is the area of totality. Next, a person standing just inside one of the inner lines still can't see the sun. This person is still inside the area of totality. Next, a person standing just outside of the inner line can begin to see part of the sun. This is where the penumbra starts. Part of the sun is visible, most is not. It will be quite dark where this person is. If we move to just inside one of the outer lines, most, but not all of the sun is visible. The person will see a lot of sunlight, but not full sunlight. This is nearing the outer edge of the penumbra. Finally, a person is just outside of the outer line, the sun is fully visible, and the person is in total sunlight. It's really that simple. All you need to know is that, barring any changes in the medium through which the light is traveling, light will always travel in a straight line. I can't think of any simpler way to explain it.
Because what's ridiculous about it is, at 93 million miles, the rays are virtually parallel and they do not spread out in space without an atmosphere.
Yes, virtually parallel. Nearly parallel. In other words, not parallel. He bangs on incessantly about the simple observation he makes using a lamp post. He goes on for about 30 seconds just to say, "Look at this lamp post." His inability to be concise is matched only by his inability to grasp basic concepts.
And let's just say we had a blocking object that was located here. So here we have an object. And what if we were somewhere in here? What kind of shadow size should we see, according to this diagram? Well, we should have something like that, right?
No, that diagram says nothing about what the shadow would look like for any object other than the moon as represented by the pink circle. If you want to know what the shadow cast by the purple circle would look like, you would need to draw new lines. In this case, there would be no umbra, just penumbra. This is because the Earth, as represented by the green line, is farther away than when the purple lines cross. If I move the purple circle closer to the surface of the Earth, there will be an umbra.
Sounds logical. Because the argument is the farther you're up in the cone, the larger the shadow that would be produced. That's why supposedly we have a 10,000 mile and greater shadow on Jupiter, because it's a little bit farther up the cone.
Sadly, he probably believes this. I've already gone over how big the shadow was on Jupiter. I'm not going to go over it again. Suffice to say, it's not even vaguely similar to what Thrivey here is saying.
So what if we were further down here, let's say in here, what size shadow should we have there? Yeah, something like that, right? So the closer we get to this focal point, the smaller the shadow would be. And then, of course, when we come out on the other side, the further we get away from it, the larger the shadow should be also.
What an imbecile. What an ultramaroon.
Do you see it? I mean, some of these at some height should have the shadow get smaller and then come back larger again. And we're going to look at the example I have of the light pole, and that is going to tell us exactly how light and shadow works with the sun when you have a larger sun that is blocking a smaller object. So you can go ahead and pause through these pictures if you want, but you're never going to see an umbra and penumbra.
Given that the penumbra increases in size at a rate of about 1/2 degree, I wouldn't expect to see a penumbra on any of these photos.
What you will see in some cases, like here, you see what I call shadow degradation.
And what the rest of the civilized world calls a penumbra. He prattles on a little more before finally getting to his actual experiment, I'll call it.
Now I'm going to manually advance through this video. Here I am standing. I'm 6'3". You can see how low in the sky the sun was to produce a shadow this long. And here is the light pole that I showed earlier in this video. And what we're going to see is, as we get way out there, we're going to see how shadow degradation works. And I'll show you an example more close up how that works also. And this is something you need to go out and do yourself, and you can actually measure this out and see. First of all, measure the pole. And I'm just going to say the pole was 8 inches in diameter. I don't know what it really is, but...
Did you catch that? First he said, measure the pole. Then he said, I didn't measure it. He's failing by his own standards.
We're just going to use that as an example. What you will find is the shadow will never be greater than 8 inches. Never.
That kinda defeats your point. First, you mock the idea that the area of totality of an eclipse is smaller than the moon, and use this as evidence that the moon is only 70 miles across. Now you say the shadow is never bigger than the pole. That really does contradict what you have to say about the moon.
Now, what you will also notice is, and this is more, you can notice it with a ball or something like that. I'm going to show you a ball that I did in another video. The shadow, when it is very close to the object, has no degradation whatsoever.
Or, as a sane man might phrase it, the further you get from an object, the larger the penumbra gets. It spreads at a rate of a little more than about 1/2 degree. We can calculate an exact value for this. Let's say that the sun is theta degrees above the horizon. The distance from a point on the pole to its shadow on the ground would be d equals h over sine theta. So the width of the penumbra would be this distance times the sine of the angular size of the sun, which is often rounded to 0.5, but is actually closer to 0.53. So W equals d sine 0.53, or W equals h sine 0.53 over sine theta. If the sun is 15 degrees above the horizon, for a point 20 feet above the ground, the width of the penumbra would be 8.5 inches and would be 74 inches from the base of the pole. If the sun is at 30 degrees, the penumbra would be 4.4 inches wide and 34 feet from the base of the pole. I don't know how high the sun was when Thrivey took this picture, but I'm guessing it was somewhere between those two values. Unsurprisingly, his video shows exactly what I've calculated.
However, once it gets beyond 1 diameter greater distance than the object itself, you start to get a little bit of degradation. It does not happen when you're closer than that. For example, if this is 8 inches in diameter, the first 8 inches of this shadow will not have any degradation whatsoever. It'll be a nice, crisp, sharp shadow. No umbra, no penumbra.
I don't know where he gets this. The penumbra starts immediately. When it's close to the object, the penumbra will be small and the shadow will be quite sharp, but it will be there.
At about 1 diameter away, you get about a 1% degradation.
I never thought I'd say this, but Thrivey is almost correct. It's actually about 1.85 degrees in the case where the sun is at 30 degrees. Less if the sun is at a lower angle.
So 1% of 8 inches would start to be degraded on the outside of the shadow. Now, as you walk this through, you will see that the size of the pole gets more and more narrow apparently. It's the same diameter all the way up. But what happens is the shadow degrades to where there is no more shadow. The light starts filtering through.
Or, phrased correctly, the further you go from the pole, the larger the penumbra becomes.
Never then comes back with an umbra penumbra where you have another, where it comes back and gets larger again. Remember,
Nor would I expect it to.
this is the same sun that is used for solar eclipses, so it should work on any scale. It should not be different just because we're talking about a smaller object. In fact, we should be able to see it easier.
Yes, it works for this pole in the same way that works for the moon. As you get further away, the umbra gets smaller, the penumbra gets larger. That's what we see here, and that's what we see during an eclipse.
So what you will notice is, let me see if I can show this here. Right about there. Let's see how much I can show here. It degrades so badly when you get out so far that it just starts losing, you start losing what the object actually was.
In other words, the penumbra gets larger than the object, and there's no longer an umbra.
More and more light bleeds through. You do not end up with an umbra penumbra. You have no sharp edge whatsoever after a certain distance.
Yes, after a certain distance, there's no longer an umbra. That's kind of what I've been saying all along.
So, according to the diagram, this should get smaller and then get larger again once we reach that focal point.
You mean the diagram that you completely misinterpreted?
So I actually did a test, and what distance does the umbra and penumbra start to happen using our sun? Well, the answer is
Immediately. Somehow I don't think that's his answer.
never. You never get an umbra penumbra. Let me explain what I have here, and then we'll be done. What I did was I took different balls of different sizes,
Giggity.
and I cast shadows from our sun onto different objects. I even did smaller balls onto larger balls onto smaller balls,
Giggity, giggity.
all kind of different distances.
The distance you're showing here looks like about 3 feet, so the penumbra would only be about 5/16 of an inch.
And I also did a video where I took coins, and started going more and more diameter distances away to show how light degradation works.
I covered this in a previous video, link in the description. If you decide to watch, the rebuttal to this starts at about 11 minutes and 44 seconds.
And if I was to zoom in on this, I'm not sure if it'll show here. Let's see what we can do here. You can see that there's a little bit of blurriness around the edge of the ball here.
Let me guess. That blurriness is about 5/16 of an inch.
Let's just say this ball is 12 inches in diameter, and the shadow is just over 12 inches, 13 or 14 inches away from the ball itself. That's when you start to get degradation.
Will he ever learn to say degradation? Perhaps he should just call it the penumbra like everyone else.
The further away you put that ball, the more diameters away, the more degradation you get on the outside.
That's right. The further the ball is from the ground, the larger the penumbra becomes.
You never, ever end up with an umbra penumbra. I challenge you. You can use the exact ratio and proportion as I did. I used a ball that was about the size of the moon, a ball about the size of the earth, ratio and proportion wise. I did the distances correct. I cast the shadow. I could not produce an umbra penumbra using our sun, which is larger than the objects I used.
And yet here you are, showing us the umbra and the penumbra. Just because you call it degradation instead of penumbra, that doesn't mean it's not a penumbra. As Shakespeare said, a rose by any other name. Although in this case I should say a turd by any other name.
So just like with the Kennedy assassination, you can use your common sense and your eyes to see that the umbra penumbra cannot be proved, ever. And during the Great American Eclipse, there was never a partial shadow.
Yes, there was. Living in Toronto, I was in it.
People want to argue, well, the partial eclipse is a shadow. No, if I take a light bulb and I cover it partially, it doesn't mean I created a shadow. It just means I diminished the light some.
That's what a partial eclipse is, you boob.
Remember, by their science, the shadow should get smaller and smaller as you go away from it, correct? As you make the blackened object further away.
You mean kind of like you demonstrated with the shadow from your pole?
Do this. Tell me if it happens. It doesn't happen, folks. All you get is the same size with light degradation around the outside.
In other words, you get a penumbra.
That's what you end up with. And you never end up with a shadow that gets smaller to a point and then comes back on the other side. I don't care what distances you use.
Nor would I expect to. That would defy every prediction made by the most rudimentary optical physics. From here, it's just a pointless recap of a pointless video. I won't waste your time with it in the same way I've wasted your time with the rest of his video. Besides, I don't know how much more stupid I can sit through. I've tried booze. I've been hitting the vodka pretty hard. It helps, but not enough. Anyway, like or don't, comment or don't, subscribe or don't. I'm going to drink some more and try to forget the stupid.